The idea of this video is to show you how we can use Excel to try and fit a function to some given data. So I've got some data in column A and column B from a run I did in Maroochydore. Okay, I've got my distance travelled, okay, and the pace. So generally just looking at the data, you can see as I go further into the run, I end up running slower. Okay, so we'll graph this. Okay, select the data, insert a scatter plot, and you can see I've got the pace on the vertical axis and the distance on the horizontal axis. And just looking at it, can't really see what the particular relationship is, apart from the fact that it's decreasing. Okay, so I'll click on one of these points. Okay, right click, I'll add a trend line, and it'll give me a whole heap of options of trend lines that I can choose. So if I think it's linear, I'll put linear in here. If I want to get the equation of this line, I could do it manually, okay, find the gradient of this line and find the intercept, or Excel will do it for me. So I want it to display the equation on the chart and also the R squared value. So I'll move this info up to the top so we can see it more easily. Okay, so there's the equation of the line. Y is my pace and X is my distance. There's the relationship and an R squared value. So R squared value tells you how well this line fits this data. Okay, 0.4688 isn't particularly well fitted. And R squared of 1 would be the data perfectly on that line. Okay, so generally anything greater than 0.7 is considered a good fit. If you get up to greater than 0.9, then you're really talking about a really good relationship between the variables. Okay, so looking at my trend line, I might not be sure that this is actually a linear function. Okay, so in this trend line function, I can choose linear. Okay, or maybe I think it's a logarithmic curve. Okay, and that'll give me a different equation and different R squared value. I can go in and get rid of that one. I can try R squared 0.57, it's better than linear. I can go to the polynomial, 0.59, even better. So order 2 is quadratic, order 3 is a cubic, not doing much better. Okay, to the power 4, a little bit better R squared value. And I could go all the way up to order 5 polynomial. Okay, and I've got this crazy curve. So 0.71, reasonably good R squared value, but I'm not going to choose this type of function based solely on the R squared value. Okay, I need to be able to actually justify why this type of curve explains why I'm getting slower as I run further distance. Okay, so I could even go up to order 6. So if we look at some of these other examples, like the quadratic for example, probably doesn't make sense for my pace to go down and then all of a sudden start coming up. Okay, unless I restricted these x values to a certain range. Okay, same thing with linear. Does it make sense that I'll just go slower and slower and slower and slower until I stop? Maybe not. Okay, so when you're choosing your function, it's a combination of the R squared value and the actual shape of the curve to determine whether or not you're going to choose that one for your function. Okay, and then you make sure you obviously format your chart. Okay, we can format the major grid lines. I think I want to format the axis. Okay, if I want to see all the way down to the origin, just like a new graphics calculator, the view window, we can change that. Okay, make sure we put a title in here, and also add some axis titles as well for X and Y, whatever the variables are. Okay.